very simple problems can have aspects that require technical sophistication in order to solve properly. Today we're going to take a look at a problem that we have all encountered. We go to a restaurant with some friends and we need to figure out how do we split the bill, except a couple of people showed up a little bit early. They ran up a very large drinks tab, and we really need to wonder, is it fair for us to pay for all the drinks they had while they were waiting for us? I guess they were waiting for us, but also they did drink a lot. Whatever the case may be, we're going to take a look at this problem from the perspective of a beginner Python programmer, an intermediate Python programmer, and an advanced Python programmer. And today, we're going to take a look at a programming problem that starts off being somewhat simple, but has a lot of room for technical sophistication. We're going to take a look at a problem of fairly splitting a bill evenly among a group of colleagues who go to a restaurant where some of them show up a little bit early. We'll investigate how the code came to be the way it is, and we'll think a little bit about how a beginner might solve this problem as well as test it, how an intermediate Python programmer might approach the same problem, and how an advanced programmer might approach the very same problem and even interrogate or negotiate some of the requirements or some of the aspects of design. In order to get started, I will share my screen with you, and so behind me, you should see my screen. I'll of course hide in the corner here. Let's take a look. This problem is titled, "We waited at the bar for like 30 minutes." Let's take a look. 3 colleagues go to eat at a fancy restaurant, and they want to share the cost of the meal evenly, except some people showed up late. While the people who showed up early were waiting, they went to the bar and they ran up a large drink tab. And so the code that we've written here, in order to compute who pays what, is subtly wrong. It tells us that everybody splits the bill evenly, with Bob paying just a little bit extra since it doesn't split into dollars and cents evenly, except if you look at it, Charlie showed up late. Should Charlie really be on the hook for this $567 drink tab? I don't think so. Let's take a look at how we would rewrite this program so that we can allocate the different types of orders that people have across all of the users who are there for that particular portion of the meal in a slightly fairer way, but still splitting it evenly, still not penalizing Alice for having a dessert or Bob for having the more expensive entree. We'll take a look at this problem from the perspective of a beginner Python programmer, an intermediate Python programmer, and an advanced Python programmer. Let's look at how a beginner programmer might solve this problem. In order to understand how a beginner programmer might solve this problem, we might want to understand how it is that the code that we were looking at got to be the way it was. And so it's very likely that a beginner might start off with some very simple code that looks like this. We have a bill represented as a single scalar value. We have the guests represented as a list of strings. We divide that evenly among all of the guests, and we allocate the remainder amount that doesn't divide evenly to one of the guests, fixing that guest. Now, this isn't quite correct because obviously if Alice isn't at the restaurant, well, she still gets that 1 extra cent. Well, this dictionary lookup will raise a key error, and so this will not only be unfair, but it'll also be erroneous code. And so very likely we want to drive who gets that extra part of the payment based off of who was actually there at the meal. We want to drive that programmatically. And so we may slightly rewrite this to do a random choice of the guests for that remainder, and this is what the first version of this program may look like. Now, when we look at it this way, we say, well, it stands to reason that what we want to accomplish is to split the bill into the portion that was served at the table and the portion that was served at the bar, and to only make the people who are there for the latter portion on the hook for the latter portion and people who are there for the earlier portion on the hook for the earlier portion. One thing that we probably might assume, especially as a beginner, is we're going to solve the problem in front of us. And so, as a consequence, we're not going to worry too much about whether Alice maybe left a little bit early and didn't get an entree. You know, as long as she was there at all, she's on the hook for the table portion of the order. The only question that's outstanding is whether or not we can make it so that somebody may not be responsible for the bar portion. And so what we'll do is we'll split the bill into 2 portions, the drinks bill and the dinner bill. And we can leave the rest of the code intact. In fact, we can just compute this evenly by summing up the drinks bill and the dinner bill. Here you can see that what we're trying to accomplish is to model a certain part of the problem slightly differently. Instead of one single scalar value for the entire bill, we model it as two scalar values for each portion of the bill. Now, if it's the case that somebody showed up a little bit earlier than the people who showed up a little bit early, we might think, well, we could extend this a bit further and we could have the pre-drinks bill. This person shows up and then somebody else shows up, and then everybody shows up, and the table is seated. And the moment we do something like this, we see that this drinks versus dinner is some kind of data-driven entity. It's not really a structural entity. It shouldn't exist as three separate variables in our program, which is something a beginner is very likely to start with, but instead look at it as some kind of composite or compound structure, perhaps some kind of list where we have a drinks bill and a dinner bill splitting up these two portions. But it stands to reason that, you know what, that there's drinks and dinner maybe doesn't include that maybe people go out for another round of drinks afterwards. And so it stands to reason that the structuring of this data should be some kind of dictionary mapping the section or portion of the meal to each one of those payments. We might store those payments as a single integer value because we may not care that the drinks had maybe 2 rounds associated with it, both very expensive. We may only care that the total bill came out to a certain amount and only certain people were responsible for that total bill. Whatever the case may be, it's very likely that a beginner might start with the absolute most basic modeling where everything is structural in nature. We have a single variable representing a single item, and slowly evolve this code to something where everything has some sort of data representation. We have dictionaries with keys. Note that this dictionary has homogeneous values, in part so that we can operate on this a little bit more uniformly. It may be the case that we want to model that there's a pre-drinks portion or many rounds of a drink, but there's only one round of dinner. But even though we may want to consider it that way, it's probably the case that having this be a dictionary with the values being a list, irrespective of whether there's only one entry or there could be multiple entries, that may be something that we do just for convenience to make the rest of this code easier. Otherwise, it might be kind of tricky to be able to say, is this a list, is this an integer, and to add that kind of confusion to this one line of code. Now, a beginner may reach for some sophisticated tools, having exposed them in other code bases or from reading the change logs of the Python programming language, or maybe even reading a blog or tutorial or watching some sort of instructional video. And so they might model the portions of the meal, the accounts that the different payments were put under, the different orders were put under in this particular fashion. And they may do something similar for the guess because they may anticipate that making the guess be a true-false value, where true represents that they showed up early and false represents they showed up late, could bite them later. Because what if we need to add in showed up really early, then a true-false no longer captures that detail. And so they may use an enumerated value so that they can start with early and late, and then later on move to really early, late, or maybe left early, and then use that to dictate how we split up this bill, how we split up the portions of the bill among the different patrons. Well, whatever the case may be, this is probably why the code looks the way it does. Now, of course, the beginner needs to solve the problem of making sure that Charlie, who showed up late, doesn't have to pay for the enormous, outrageous drinks bill that Alice and Bob rang up while they were waiting. And so the beginner may accept this modeling or may accept the evolution of this modeling and work within that framework. This is something that we often see that beginners do, and it is a reasonable thing to do if you are a beginner. That is, you're given some code, and you're not really willing to push the boundaries of how that code models the underlying physical reality. And as a consequence, you try to get something to work within the constraints of how the problem is actually set up. Because you're not willing to go back to the stakeholder and say, you know what, I don't like the way we've stated this problem. I don't like the problem we're trying to solve. We shouldn't solve this problem at all, or we should solve it very differently or conceptualize it very differently. You're more willing to just accept it as it stands. Unfortunately, this oftentimes leads to unbounded technical sophistication where, in order to accept the formulation of the problem, you have to do some really weird things in the code to get everything to work because you're just not willing to push back and say, you know what, let's solve a different problem that just melts away the technical sophistication. Well, in this particular case, the code isn't that complicated. There may just need to be 2 loops where we identify who the bar guests are and iterate over the bar guests. We identify who the table guests are and iterate over the table guests, and we split those up individually. Note that this is not atypical of beginner code. Namely, that even though the underlying modeling of the parts of the bill was some kind of data-driven structuring, that is to say, we could imagine adding in extra entities here, it still may require extra entities being added into this code. Note that if we added in one more section, like pre-drinks, this code would be wrong because we didn't account for that with another loop. And so one thing that the beginner might be encouraged to do a little bit better in this code is to take these two loops and to turn this into a loop that actually operates on the parts of the payment or the parts of the order that are found in the input data, as opposed to hard coding that there's either a bar bill or a table bill. But whatever the case may be, this does in fact solve the problem put in front of the beginner, and the beginner may say, you know what, let's write a test for this. Now, it is very common that the beginner may write an expected versus actual test or an oracular test. In truth, even intermediate or advanced users are often somewhat lax in their testing of the code. In fact, an advanced user may oftentimes, just out of expedience, out of lack of time, out of a rush to meet some deadline, just write a code that or a test that looks like run it once, see if the output kind of makes sense, and move on with my life. But of course, if this is an important problem, then it's probably important that this problem is solved correctly. If this problem is important to solve correctly, then we need some mechanism to assert that correctness, whether that mechanism is something like type hinting, something like manual testing, or some kind of automated testing, or some combination of those three. And so likely, we might end up with some kind of test, but note that this expected versus actual or oracular test, well, the downside of this is it really isn't altogether that much different than a test that is performed manually. It really is just kind of saying, okay, here's some input, here's some output. Do they match up? Does the expected match my actual? Now, a very important detail of this test, and the reason why we like to call these oracular tests, is the only way we can conceive of a test like this is if we have an oracle that tells us, given these inputs, this is what the answer will be. Well, the oracle in this case is either a prior run, we ran this code and just accepted it to be right, or desk checked that it would be right, and then hard-coded that output, or I don't know, maybe we have an alternate means in order to solve this problem. Maybe a human being can calculate the answer and then check that against what the program has. But whatever the case is, the test itself can't really test anything in the absence of somebody saying, oh, you know what? Given these inputs, these are what the outputs are. And this means that the only way for us to create test cases is for us to conceive of some inputs, compute the outputs for those, and then to match them up. Well, this is a very limited approach because we may not be able to conceive of test cases that find all the different regions within the input domain such that we check for all the special cases or corner cases that might arise. For example, what if there is no bar bill? What if there is no table bill? What if there is a bar bill but it's an empty list? What if there are negative values? What if there are floating point values? Considerations like that. And we have to really conceive of those diligently by thinking through, okay, what are all the partitions of the problem? Maybe using something like test coverage in order to guide us. Oh, I see this branch of the code wasn't taken, so that probably means that I don't have a test case that I need to have. And you can imagine this is very limited because it relies on human fallibility. Well, with a better testing approach, using something like hypothesis, we no longer need to be as diligent at finding where all the boundaries of the partitions of the input data space are. Instead, we use some heuristic to guide us to find random sampling or heuristic-guided sampling of inputs. And then we write our test not in terms of some oracle, but in terms of something that we can assert on properties of how that test operates on some inputs or how the function operates on some inputs and some outputs, or how the outputs may change based off of changes in the inputs. Whatever the case may be, that more sophisticated testing may be reserved for an intermediate user, an advanced user, or somebody simply who has a little bit more time. Do note that this test is wrong. Even though, or rather I should say the code is wrong, even though this test isn't that great, it still is able to catch a real issue in this code, which is to say that sometimes this test fails and sometimes this test succeeds because the underlying code is non-deterministic. Now, this is a little bit odd because you can see here that in the code they passed in a random state. And if I run this enough times, I'll eventually see a running or working example of this code. Here, let's run this here. And we'll see this run and succeed at least once. There we go. Well, the problem is that even though we have passed in a random state and we're doing the random choice on this, we're doing a random choice of a structure that we've turned into a list where that underlying structure is a Python set. And unless we set the Python hash seed, which requires that we set this outside of the running program, well, the ordering of the elements in this set will be determined by some additional seeding of the hashing operation that assigns where these elements will be in the contiguous data for the set. And so as a consequence, we can have some non-determinism creep up. It's probably the case that we don't want to set that hash seed for the purposes of testing because that might cover up other issues. And so instead, a very, very subtle change may need to be made to this code, specifically that if we do a random choice on something that is not human ordered, we might first need to sort it in order to make sure that we always get a deterministic choice from that ordering. And if we do that, we might eventually get a test that consistently always works. Of course, we'll have to update the test to figure out exactly what the ordering of who pays the extra amount might be.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.